Let's look at depth-first search. And we're going to see how to use depth-first search for topological sorting. But as a simpler motivation for depth-first search, you can also consider the problem of cycle detection. So a cycle is a closed path in a graph. And if we want to know whether our graph has a cycle, then we can use depth-first search to find it. So what is depth-first search? Many of the concepts here are the same as for breadth-first search. So if you haven't seen the video on breadth-first search yet, I would recommend watching it now. The interesting part is this breadth-first search visit here. So it's a recursive algorithm which, starting at a vertex u, visits the part of the graph reachable from u. But here we want to visit the whole graph. To make sure that we do so, we have also this, you could say, outside algorithm, which whenever we are done with a part of a graph, we then restart it at some white vertex. And the concept here is a concept of time. So we have a global timestamp, and we're going to use this to denote when we see a vertex first. So that's the discovery time of that vertex. And when we're done with a vertex, that will be the finishing time of that vertex. And you see here d of u and f of u, those will be the discovery and the finishing time of u. So let's have a look at this in a bit more detail before we look at an example. So first of all, depth-first search visit starting at u. So we will color u gray. This is the time where we discover u. So we're going to set that to the current time. We increase time by 1. And then for the adjacent vertices of u that are still white, we're going to set u as predecessor of v, so just as in breadth-first search. But now we're going to immediately visit these adjacent vertices. And then when we've done that, so if we come back from the recursive calls of depth-first visit for the adjacent vertices, then we're going to color u black. And then we're done with u, so then we're going to set the finishing time of u to whatever time we have then, and increase time by 1. So note that because we had these recursive calls in between, the time will have increased by now if there were adjacent vertices. So that's the depth-first search visit. And then as kind of the outside algorithm, we initially make all vertices white, set their predecessors to none. We set the time initially to 0, and then we start at some white vertex and start depth-first search visit. And when we come back from that recursive call, there might be white vertices left. So then we take one of those, continue again, and so on. Let's do depth-first search by example. So we first color everything white. Then we start at whatever vertex we encounter first. Let's say that is a vertex 1. So we color it gray. Discovery time is current time, which is 0. And we recursively call depth-first search on its first adjacent white vertex, which is 2. So we color 2 gray, it gets 1 as predecessor, discovery time is 1. We immediately call recursively depth-first search visit on whatever we see in the adjacency list of 2 first, which is a 5. So 5 is gray, has 2 as a predecessor, discovery time of 2. We again immediately call depth-first search visit on. So 5 still has 4 as a white adjacent vertex. So 4 has 5 as a predecessor, discovery time of 3. Now there are no white adjacent vertices for 4 left. So we're immediately done processing 4. So it will get a finishing time of 4. It has a discovery time of 3, finishing time of 4. We color it black. So when we were at 5, we recursively called depth-first search visit on 4. Now we're coming back from that recursive call. There's nothing else to be done for 5. So it gets as finishing time the next timestamp, which is 5. We go back to 2. Also for 2, there's nothing left. So finishing time of 6. For 1, nothing left, finishing time of 7. So now we have time 0, 1, 2, 3, 4, 5, 6, 7. We're coming back from the depth-first search visit on 1. So now we're back to the global algorithm. There's still white vertices, well, so we go to whatever white vertex comes next, so that it will be 3, discovery time of 8, recursive call will bring us to the 6, which has 3 as a predecessor, discovery time of 9, finishing time of 10, because there's nothing else to be done there. We come back from the recursive call on 6, back to 3, nothing to be done, so finishing time is 11, the algorithm is done. And because we kind of always restart on white vertices, depth first search will always visit all vertices. Let's make some observations about depth first search. First of all, depth first search explores all vertices. It also explores all edges, even if we don't do a depth first search visit via those edges. So, and that's all that it does. So the running time is order of vertices or number of vertices plus number of edges, so order v plus e, assuming that we have the graph as adjacency lists. Then what we get in terms of these green edges, or in the terms of the predecessor edges, is a depth first forest. So what is a forest? A forest is a collection of trees. So we get one or more depth first trees. And the trees are comprised of the edges uv with the property that when we explored that edge, u was gray, v was white. And we can more generally classify all of the edges of the graph. So first we have these tree edges. So those are the ones that when we looked at the edge uv, u was gray, v was white. So meaning that when we first discovered v, this was the edge via which we did it. And those are the ones that form the depth first forest. So those are the ones that you see here in green. Then we have back edges. So what is a back edge? A back edge is an edge uv that connects a vertex u to an ancestor in the depth first tree. So as an example, this edge here connects the 4 to the 2, and the 2 is an ancestor of the 4 in this tree. So the tree goes from here down to there, and then the back edge goes back up. And just as we have back edges, we also have forward edges. So a forward edge is a non-tree edge which goes from an ancestor to a descendant. So here, for instance, this edge here, it's not a tree edge. So the purple edge here is not a tree edge. It goes from the 1 to the 4, so from an ancestor to a descendant. And then the final type of edge are the ones that do not go between ancestors and descendants, and those are the cross edges, and we have an example of a cross edge here, that orange edge. Here's once more an example. If a graph is undirected, then we won't be able to distinguish between going backwards or forwards. So then we will simply call those edges back edges, and cross edges will simply not occur. So we have, for an undirected graph, only tree and back edges, and for a directed graph, tree, back edges, forward edges, and cross edges. Another property that we're going to explore in more detail in a moment is that discovery and finishing times have parentheses structure. So what does that mean? It means that the following cannot occur. So it cannot happen that I discover a vertex, I discover another vertex, now I finish the first vertex, and only then I finish the other vertex. So that cannot happen. So if I discover a vertex and then discover another vertex, then I first need to finish that other vertex before I can finish my first vertex. More about that in a moment. Let's first have a quiz about the edge types. So which of these edge types shows us that there is a cycle? A graph has a cycle if and only if it has a back edge. So let's just do that by an example. So if I have this cycle here, then if I start exploring my graph here, I will have a tree edge, I will have a tree edge, and at this point I will have a back edge, and at this point I will have identified a cycle. Now let's have a closer look at the discovery and finishing times, and in particular the parenthesis structure. So here was an example that we had. So let's see whether the parenthesis structure works here. So if I look at vertex number 1, so it starts at ds0, it ends at time 7. Vertex 2 starts at time 1, it finishes at time 6, so here we have the parenthesis structure. 2 and 5 is here, so that's also fine. 3 and 4 is also fine in terms of parenthesis structure. Now we have 8 and 11, so that's actually after 7. So that's here. 9 and 10 is inside of that. So as you see, we have a valid parenthesis structure. And this holds in general. More specifically, in a depth-first search, if I look at two vertices, u and v, then I will have one of the following cases. So now I'm looking at the interval du fu, so discovery and finishing time of u, and discovery and finishing time of v. So either those two intervals are completely disjoint, so either u completely first and then v, or vice versa. In that case, neither u is a descendant of v nor v is a descendant of u in terms of the depth first forest. Or I have v, so the interval for v inside of the interval of u. In that case, v is a descendant of u, or vice versa, the interval of u is inside the interval of v, then u is a descendant of v. In particular, what that means is I cannot have a case where I have the discovery time of v, then the discovery time of u, and then v finishes before u finishes. So let's sketch a proof of this, and we're going to assume that the discovery time of u is smaller than the discovery time of v, otherwise we can switch the roles. And now we have two cases. The first case is v is discovered in a recursive call of u. So you can imagine you have u, we do a recursive call, and at this point, at some point, we reach v. So what does that mean? It means, first of all, that v will be a descendant of u. It also means that if we want to finish the recursive call of u, we will first have to finish the recursive call on v, meaning that the finishing time of v will be smaller than the finishing time of u. So here we get the parentheses property. The other case, so we have now the case that v is discovered during the recursive call. So the other case is that v is not discovered during the recursive call. That means that v cannot be reached from u. I mean, keep in mind the discovery time of v is larger than one of u. So if it would have been reachable from u or of any descendant of u, then we would actually have explored it. That means that v will only be discovered after I finish the recursive call for u, but that then also means that the finishing time of u will be smaller than the discovery time of v. So what does it mean in terms of the descendant relation? So we already observed v is not a descendant of u, but u can also not be a descendant of v, because when I start processing v, u is already done. And that is the proof of this parenthesis structure. So before we put this into use, let's have a quiz. And the quiz is the following. Assume I have a graph G, which is only a path from u to v. So which of the two vertices, u or v, has the larger finishing time? Is it u, is it v, or does it depend where I started my depth first search? U has the larger finishing time. Let's see that by example. So here we have a path. This is u, this is v. So let's assume we start our depth first search somewhere, let's say here. Then we will color it gray, go to the next one, and so on. So at some point we'll reach v, we'll discover it, we will immediately finish it, and then we will work our way backwards. So that means v will be finished first. It will be the first one that is finished. And that is no matter where I start. Even if I start at u, then I do recursive calls until I reach v, finish v, and then work my way backwards. So u will be the one with the larger finishing time. And this idea we're going to set into use in the following problem, topological sort. The problem of topological sort is the following. The input is a directed acyclic graph, like the execution order for processes here. And the output should be a linear ordering of the vertices, so a numbering of the vertices v1, v2, and so on, such that all edges go from a smaller index to a larger index. The idea here is that we often use directed acyclic graphs to model partial order. So what is a partial order? It means that if we have that A should be larger than B, or A is larger than B and B is larger than C, then A should be also larger than C, but not all elements are comparable. So there are elements, or there can be elements such that neither A is larger than B nor B larger than A. Now here in terms of partial orderings, our problem is that we want to turn a partial order into a total order. Let's see this by example. So here we have a directed acyclic graph. Now we want to label the vertices v1 to v6 in this case in such a way that edges go from smaller index to larger index. So if I lay out the vertices in this order from left to right, so v1, v2, v3, v4, v5, v6, then the edges should also all go from left to right, and that is indeed the case. So this would be topologically sorted. In contrast, if I would additionally have this edge here, then this would no longer be correct. I could still repair this, but that ordering here is not a correct order. Generally, any directed acyclic graph has a topological order. And only if it's acyclic, then we have a topological order. So for general directed graphs, what we can do, we can run depth first search, and either we find a back edge, then we know there's a cycle. Otherwise, it's acyclic, and then we will get a topological order, and we will see how we get it next. It's very simple. We call depth first search. This will compute finishing times for all of the vertices. And now we simply output the vertices in decreasing order in terms of the finishing times. So let's look at this as an example. So here we have a morning routine and dependencies between those. So someone is getting dressed, and for instance, you should be putting on the socks before you put on the shoes, or the shirt before you put on the tie. The depth first search starts somewhere. Let's say it starts at the shirt. We can continue with an adjacent vertex, a tie, with an adjacent vertex, a jacket. The jacket doesn't have any white adjacencies, so we finish the jacket, we finish the tie. The shirt still has a white adjacent vertex, namely the belt. Now we finish the belt, we finish the shirt. Now we have to restart somewhere. Let's say we restart with the watch. Okay, there's no edges, so we finish immediately again. We continue with the underwear, we continue with the pants, the shoes, no outgoing edges, so the shoes are finished, the pants are finished, the underwear is finished, the socks remain, we discover them, we finish them. Now, we wanted to order them in decreasing finishing time. So just to observe here, the largest one is 18, so we would be saying, let's start with the socks. We continue with the underwear, we continue with the pants, we continue with the shoes, maybe a bit unusual, but it works, it seems. We continue with the watch, shirt, belt, tie, jacket. At least that makes perfect sense. So here we have our linear ordering of this morning routine. We should analyze this algorithm. So first observation is this algorithm, given a directed acyclic graph, actually produces a topological sort. Why is that the case? We're going to do a proof by contradiction, and we're going to use the parenthesis structure of the discovery and finishing times. So what does proof by contradiction mean here for us? So we're going to look at an arbitrary edge, and we want to show that it points from a smaller index to a larger index. So we need to show that f of u is larger than f of v, because then it goes from a smaller index to a larger index, because we have the vertices in decreasing finishing times. So to prove this, we're going to assume the opposite. So let's assume f of u is actually smaller than f of v. Now let's look at these intervals. So f of u is smaller than f of v. So there are two cases. Either we have this nested structure, or f of u is completely before f of v. So if we have this nested structure, what does that mean? it means that U is a descendant of V. But that means that G has a cycle, because this means I can go from U somehow to V. I mean, that it means that V is a descendant of U. But also I'm saying I have the edge UV. And overall that gives me a cycle. So that's a contradiction for this case. Now the other case is that I have the structure like this. But then when I visit U, V hasn't been discovered yet. But that means that when we call depth first search visit on U, we should also at some point examine the edge UV, and at that point would, during the recursive call of U, discover V. So we cannot get this parenthesis structure. So also this case cannot happen. So overall what we showed is that if we have an edge UV, then f of U is larger than f of V, meaning that if we sort by decreasing finishing times, then we actually get a topological sorting. Okay, so we know the algorithm is correct. What is its running time? Now we have to be slightly careful. I mean, we said we sort by finishing times or by decreasing finishing times. Of course, sorting as such would take n log n time, but we don't need to actually sort. So while we do the depth first search, as soon as we finish a vertex, we simply place it in the order. And in that way, we simply take as much time as depth first search takes, and that is simply order V plus E, and then order V additionally still for outputting. Overall, that's order V plus E. That's the running time for topological sorting. Let's have a quiz about this. Given a graph G, is a topological sort of that graph unique? Yes, always. No, never. Only if G is a path that goes through all vertices, or only if G contains such a path, A, B, C, or D. The correct answer is D. The order is unique if and only if G contains such a path. So if G contains such a path, the only way to lay out the vertices is by respecting that path. Otherwise, one of those path edges will be pointing backwards. On the other hand, let's assume G does not have a path. Then obviously, if I lay out the vertices, so if I do the topological sort, then I cannot have edges between all of the adjacent vertices, because otherwise that would give me such a path. So let's say I don't have this edge, but then I can easily swap those two edges without messing up the topological sort. So D is the correct answer here. So what have we seen overall? We have seen graphs, we have seen how to represent graphs, we've seen breadth first search, and we've seen depth first search, and as application of depth first search, topological sort. That's all for today. See you next time.